I want to add a little bit of information within the context of Chapter 7. It is literally, you just need to do. Okay? This is kind of memorization stuff at this point. Okay? So if it says do an SN2 reaction, you do an SN2. You look at it and like, I don't think this should do it. I don't give a crap what you think. If it says do SN2, you do SN2. Okay? So there's no why, there's no challenge. This is what it is. Okay? And I would argue at this point, you don't have them memorized, so you shouldn't be sitting there, oh, what do I do for an SN2? How should this work? No. Pull up the notes, look at what SN2 is supposed to be, match it. Okay? So the structures will look different, the pieces will look different, but you just need to match. Okay? So when we talk about the SN2, we'll provide some background context behind it. In the SN2 mechanism, okay, first and foremost is it's a substitution reaction. And when we look at the substitution reaction, two things happen. You get the loss of a leaving group. We'll come back what that means. And then a gain of a new atom, and that new atom will reference as a nucleophile. Okay, so substitution does those two things. And SN2 does those two things at the exact same instant. Okay? Each thing minimally is going to require a curved arrow, which means if you're being asked to draw the SN2, you're going to need two arrows. Okay? LG, I said, was leaving group, and I abbreviated it. Good job, Mike. And then I write it really sloppy, so you can't read it anyway. But it says leaving group. Okay? What do you think a leaving group should do? It needs to leave the molecule. The question becomes is how does it leave the molecule? Okay? Should it leave with the electrons, or should the electrons stay behind? Okay? And ultimately what this is coming down to is just the definition of what a leaving group is. The leaving group, by definition, takes electrons. Okay? So I understand where you're going, like it depends. Technically, it doesn't depend. The leaving group will always take the electrons. Okay? Where things can get a little bit weird is that you may go through and you see a structure and the leaving group is really, really, really big. We don't care. Size is irrelevant. If it took electrons when the bond broke, it was the leaving group. We don't care how big or small these things are. It always takes the electrons. Okay? So we can now go to our first box, and we kind of want to address what's going on within it. Could the iodide be a leaving group? No, why not? It's only one atom. It can't leave from anything. So by definition, our leaving group cannot be the iodide. It's got to be something within the other structure. Okay? So now we should go through and look at that other structure and say, well, what things could leave? Okay, well, I've got a carbon up here, right? Would I expect that carbon to leave? Okay, so some people are immediately saying, no, why not? Why can't it leave? Why not? Why can't I have just carbon leaving? What would the result look like? Okay, since you're all shouting it out at once, I'll give you time to actually draw this out. So draw it out, pencil and paper. If I don't think you're drawing it out, pencil and paper, for the record, what we're going to start to bring in, because now these are conversations about how things work, what we're going to start to bring in is board work. Everybody loves getting up and drawing on the boards, and we'll make everybody get up and draw on the boards.
Sounds fun.
Most people will kill you for that, so
Really?
keep your mouth shut.
You just draw shit.
I know. Just draw on your board paper then.
Hey, toddler.
So if we're just going to draw out what that single arrow motion means, what we're drawing is something like what I've got up here on the screen right now. Okay? It's got some problems, so let's address some of those problems. First and foremost, that C up at the top does not have a complete octet explicitly shown. Okay, so if I'm going to write out a C down here, I should make sure that my octet is directly addressed. We have to realize it's only showing 2 electrons around it, which means there's 3 implied hydrogens, which means I should have those 3 implied hydrogens also tacked to it. The electrons in that bond went to that carbon. That's going to be a pair of electrons on it. That's a lone pair. Okay? So cool. What we've done at this stage is just showed where the electrons move, which shows some understanding of the Lewis structure. But we have to realize the last step of every Lewis structure is account for your formal charge. So you should be able to go back and now double check what's going on with your formal charges. That carbon is going to be negatively charged, and the carbon where the structure left from is going to be positive. Okay? That's what that single arrow means, period. Okay? So if we're asking the question, should it do this? Okay? That's a much harder question, and arguably not a question that's being asked within this particular circumstance, but we're going to lean into it anyway. Andrew's super confident and says it should not happen. Why not?
Because if this was true, all molecules would do this, right? Have we seen anything like this at all? No. That's my reasoning.
How many times have you seen even this period? Okay. Just the structure to begin with. Have you seen? So you've seen nothing of it ever, and so your argument is because you've never seen any of it, the entire class didn't exist.
Yeah.
Yeah, it doesn't work that way, sorry. Okay, nice try, but no. Say again? Sort of, yes, it has to do with charges. What about the charges do you want to lean into?
In that it's not stable.
What's not stable? Which charge? Because there's 2 charges.
Then negative.
The negative charge you want to say is not stable. Okay, why not?
They just attract right back to each other?
Okay, they would attract right back to each other, which is ultimately going back to your statement. They're not stable on their own. They're going to immediately come back. But again, why? Why should they immediately come lock back? Okay, so to Andrew's comment of, well, it's never done this before, so it can't do it. They do actually aggressively do this. Okay, but it's an equilibrium reaction. And in that equilibrium reaction, how do our arrows align? Whoa, I don't know what I just erased. Hopefully we didn't erase anything important. If we were to look at this as an equilibrium, it's this. That's a tiny arrow going towards the bond breaking. Okay, this reaction very swiftly goes right back to the reactants, which means the net result is we don't see this bond breaking. Okay, again, the question becomes why? Because you think something about the products is unstable. Okay, why? Why are they unstable? Octet. So we could make an argument about octet for the positive charge. Okay, I would kind of counter that the octet really isn't that big of a deal because I could have the bromine do resonance and donate electrons into it to stabilize that carbocation. Okay. Officially, really what this is going to come back to is 2 kind of principles. Number 1, dealing with the equilibrium constant, and the equilibrium constant is a fancy way of saying we've tested this experimentally, and this is what happens. Did anybody want to evaluate the equilibrium constant, i.e. revisit all of the stuff you learned in 152? No. Okay, so we don't want to do that. Instead, what we want are some baseline rules that would help us to explain why we would not do this versus something else. Okay, we could go through and look at the carbocation and say carbocation, not particularly great. We don't like carbocation. It's resonance stabilized. Yeah, okay, the carbocation is not a great space to start. How about a negative carbon? Okay, how stable is that? What would stabilize a negative charge? Okay, a positive is coming in from the outside. What we have to do is what would stabilize it internally? You're talking about it reacting somewhere else. I don't care about somewhere else. I care about negative carbon. What would stabilize a negative atom? And part of that, I think, that's confusing is you're not having something to compare it to. Okay? So we can do another sidestep. We'll sidestep the why here question to get back to the overall question. It says we need to complete the SN2 reaction as shown. As shown, what left the structure?
Bromine.
Which means, is the arrow we've shown correct? No. So we can use the context of the given information to say we're wrong. Okay, kind of makes sense? Okay, we're going to come back to that why question, why this path was a bad path and why the other path was a good path in a second. Okay, so our leaving group can tackle anything around that carbon structure and anything can leave. Because we're given the products, we know what left. We know it had to be Br minus, or it had to be the bromine, which means what we're going to do is focus our intent on the electrons in that bond. Those electrons need to go to the bromine. Why should they go to the bromine? Two very good answers that can come out of this. The first answer, bromine is more electronegative than carbon. Hell yes. That's a fantastic explanation for why the electrons should go to the bromine. There's a cop-out answer. What's the cop-out answer? What is the bromine acting as? A leaving group. And the leaving group always takes the electrons. So we get two explanations for why we can go through and say that that bromine needs to take the electrons away. Okay, absolutely makes sense. The why part of that is bromine is more electronegative than the carbon. We'll take the electrons away. Okay, what happens with that result? Well, we'd get our Br minus, right? So there's our Br minus. It would pick up that lone pair. Officially, it already had lone pair electrons. We're probably going to have to come back to that in a second. Okay, what happened to the carbon on the other side? Same thing that happened to it in our other drawing. It had to become positively charged. All we're showing is that single arrow, the leaving group leaving. Okay, we're breaking that leaving group bond. That would be the result of that single arrow. Okay? Why do we know the bromine had to do it? Because we looked at the product. That's the only way we could get Br minus chilling out on its own, is if that bond broke. And it broke in the way we're showing it with the arrows. Does that make sense? We're going to make it harder. Why is the bromine reaction better than the carbon reaction we did? We're evaluating the stability of the electrons once our structure has left, or once our leaving group has left. Bromine is better able to stabilize, technically bromide is better able to stabilize that negative charge than the carbon. Why? They both have the same charge. What we would do is move through our list of rules on deciding stabilities. We start with charge, we move to size. Bromine is larger. Because bromine is larger, it can stabilize the negative charge better than the carbon, which means it makes more sense for the bromine to leave the structure than it does for the carbon to leave the structure. So while we could have carbon leave, it's not going to result in a stable enough structure, okay, based off of the comparative other outcomes. That means the initial error that we drawn with the carbon leaving was a bad idea and we shouldn't have done it. That's the why component. Kind of, sort of? So cool. If we go back to the question, it just said we need to draw arrows. So I draw that arrow. Ta-da! Bromine's left. I've done an SN2. No. The SN2 required two things: the loss of the leaving group and the gain of the nucleophile. Right? If we go through and look at the system and we unhide what I'd put in there, that's what we were trying to make. We needed to make those products. We've shown the formation of the bromide, but did I show the iodide do anything? Nope. So I need another curved arrow to explain how it's doing something. What is it doing? I have to gain a nucleophile bond. Iodide is negatively charged. What do we need to stabilize a negative charge?
Or into a bond. You look at it in the
True. But what is that thing that I need to form with?
a positive.
It would need to be a positive charge. I need a negative to be stabilized by a positive. What things are positive?
Okay, on that forms.
What subatomic particles are positive? Protons. Where are positives located? Protons located. In the nucleus. You mean the iodide is a nucleophile? Yes. The iodide, having a source of electrons and willing to share those, is going to hunt for a positive charge. It wants to be next to it. Where's that positive charge? I don't see a positive charge in my structure, except that, what is that bromide doing?
Forming a positive charge as it takes.
Taking the electrons away from the carbon, making the carbon partially positive. So the iodide now needs to share its electrons with that carbon at the exact same instant that the bromide takes the electrons away. Why do I have to do it at the exact same instant?
Because wouldn't the bromine just stay there using the same?
Nope. Why do I have to do it at the exact same instant? Nope. It's nothing to do with other things. What's that? Nope. I know it has to happen at the exact same instant because what am I told? This is an SN2 reaction, and when I do SN2 reactions, I must lose the leaving group and gain the nucleophile at the exact same instant. It is the definition of an SN2 reaction. So you must do that. That's why you're doing it. Okay? Can we get deeper whys? Yes. Wait till next week. Sort of wait till lab, actually. Okay? So for this particular question, what am I doing? I'm having the iodide come in. I'm gaining the nucleophile bond to my carbon. And so the gain and loss are all relative to the carbon structure. Why? What class are we in? Organic chemistry. And organic chemistry is all about our carbon structures and ultimately the electrons around them. Right? So our focal point is always the carbon. When we talk about loss of the leaving group, we're talking about the loss of the leaving group from the carbon structure. When we talk about gaining a nucleophile, we're talking about adding atoms to the carbon structure. That carbon structure is our focal point for all of this. So if I want to draw out what this says in SN2, I need to add the curved arrow where I start from the iodide. I have it react with that carbon. We're going to run into some fat arrow issues here. Where is that blue arrow trying to point to? That center carbon. Okay? Real hard to do pencil and paper. SmartWork does it really well because it snaps to wherever you're trying to take it to. So if you want to take it to the carbon, you have to hover your mouse cursor, you click your arrow from iodide, and you click and drag to wherever you want to drop the arrow point. And when that carbon atom is highlighted, now you can drop release. You have an arrow showing that connection. Okay? And if you don't do that and you try and drop it without specifying where the arrow is going, what happens to your arrow? It disappears. So you can't have floating arrows. You have to define exactly the beginning and the end. So I need that arrow, and I need the arrow from the carbon-bromine bond. Again, I have to be very selective. I'm talking about the electrons in the bond, so I'll click on the bond and draw that going to the bromine. Okay? That would result in the formation that we have out here at the end. Okay? And if we entered that into SmartWork, we'd be told we are wrong. Why? Because we didn't read the frickin' question. If you go through and read the question, what does it tell you to do?
Draw the arrows.
Draw the arrows. Yes. Add lone pair electrons and non-zero formal charges. So if we go through and look at those two boxes, we don't have any lone pairs explicit, so what you would have to go through and do is make sure that you also add that iodide has 4 lone pairs. How do we know it has 4 lone pairs?
It's a negative charge.
Because we memorized our common bonding patterns, and for iodide to have a negative charge, it must have 4 lone pairs. How many lone pairs are on that bromine? It has 3 lone pairs because common bonding patterns, again, for our bromine. This is why it was so critical to have nailed that down in the first unit. Okay? Now what happens when we draw out the products? we still have to account for the lone pairs on the iodine. Now we only have three, not four, because the fourth went into the bond. What happened to the bromide? It should now have 4 lone pairs. We've accounted for now all of our lone pairs. Do we have our non-zero formal charges? Yeah, for whatever reason, they actually already gave you those. Right? We don't have any positive charges. The carbon structure doesn't change its charge because it has both lost and gained electrons. So there's no changes there. I now have a correct answer. Kind of makes sense? One of the biggest hang-ups that you're probably going to encounter within SmartWork is the drawing of lone pairs. Okay, almost invariably people want to avoid drawing the lone pairs. I get it. I understand. I don't draw lone pairs half the time. Okay? But the point or the reason why I don't draw lone pairs is I don't screw up my mechanisms because of it. You're currently learning that process, and what's going to end up happening is you will screw up your mechanisms because you don't have the lone pairs explicitly drawn. So make sure you've got them there. Make sense? Does that answer your question okay for this one? Okay.
Could we do elimination one?
Sure. I feel like I had a different question, but I don't remember. The homework question set is now a lot more involved because it's not asking a single mechanistic step. We're now stringing 3 of these things together. Okay, so what we want to try and go through and do is process through based off the information that we have at hand. Okay, so first and foremost, the first thing we want to do is the first step. That's generally where you start is the first step. So the first step in this case is E2. What does E2 mean? Cool. E means elimination. What does the 2 mean? That gets a lot harder. Again, context, you don't necessarily need to know that yet. Wait a week. Okay? And it becomes important. You need to actually eventually know that. That 2 means a couple things. Officially, it means bimolecular. Have you heard of bimolecular before? Okay. This is where everybody should shake their head. Yeah, I totally remember bimolecular. Okay. Let's switch it up to a slightly different question. Have you heard of second order? Okay. Everybody should be a lot more aggressive. Yes. And we talked about orders for chemical reactions. That showed up in 152. That was chemical kinetics. Okay? How important was that relevant reagent? Bimolecular means there were 2 things in your kinetic expression for your rate law. If it says elimination bimolecular, what does that mean? There are 2 things in the rate law. It means the exact same thing. Okay? What are the 2 things that are important for the elimination bimolecular? I need to lose H+, and I need to gain a pi bond. This one actually gets trickier. Lose H+, gain a pi bond, and loss. Oh, that's why I'm having a hard time. Lose a leaving group. This one gets a little bit tricky because we now have 3 different things going on at the same time. Okay? When we look at the logistics behind this, I would actually argue it's really only 2 things that are happening at any given instant. But those 2 things happen in a proper organization next to each other that allows for this chemical reaction to happen. Right? So I need to lose H+, I need to lose a leaving group. How can I go through and do this? Well, which would you rather look at, the H+ or the leaving group?
Leaving group first.
Cool, leaving group, which means we can go to our starting structure and say, what thing would I expect to leave this molecule? Chlorine. Why chlorine? Are there other choices?
It could be hydrogens, but
What do you mean there could be hydrogens?
there are hydrogens.
Okay. Remember, we have implied hydrogens in all of these cases. So if we're talking about leaving groups, since it's a cyclic molecule, we should really only be talking about things that could leave on the outside. Technically, we could actually talk about leaving groups within. If I break that bond of that ring, that is technically a leaving group. It never leaves the molecule, but it leaves the atom to which it was connected. That gets real tricky. It's intramolecular. Let's not stress about that yet. So which is the better leaving group? Chlorine or the hydrogen? Okay, why chlorine? We can push to electronegativity. Remember, the leaving group, by definition, takes the electrons with it. So we'd be looking at either chlorine, picking up the electrons, or hydrogen. What we're talking about is Cl- versus H-.
Would be more stable on its own.
Which one is more stable? H- or Cl-? Cl, because it's bigger. Size. Charge, size. Size is going to play a huge role. Not intended. Pun, words, whatever. Okay? Initially, because that's a relatively easy example for people to work through. Okay? So hydrogen doesn't make sense to act as a leaving group. We're going to have our chlorine act as the leaving group. Stupid stuff underneath. Okay? What would that result in? If we just did that one arrow.
A negative chlorine and a positive cation.
We should get a negative chlorine and a positive carbon. Officially, we should make sure that we have the lone pairs because it probably says that up in the directions. Okay, I'm not seeing it in the directions, but it might be in the individual boxes. Okay? You're just taking notes, right, Serenity? Not trying to draw it in?
Taking notes.
Okay. I just want to make sure you weren't trying to draw this as your answers yet. It's not a good idea yet. Okay? So cool. What we've done with this is shown what happens if we lose the leaving group. That's fantastic. Okay? Have we shown an E2? No. Why not?
It's got a pi bond.
I don't see the formation of a pi bond, and I haven't seen the loss of the H+. Okay? So now I've got to figure out what do I want to address. Okay? I'm going to argue that the gain of the pi bond is actually irrelevant to the overarching mechanism, and we can ignore it. There's really only two things that are happening. I need to lose a leaving group, and I need to lose that H+. Since we looked at the leaving group, now what do we got to do? We need to look at the H+. Okay? So somewhere on this molecule, there needs to be an H+. Okay? For there to be an H+, what has to happen? So let's look at an H. Ta-da, there's an H. If that was an H+, how did it become positive?
Lose its electron
The electrons. Where did the electrons go?
to the main atom itself.
They went to the atom that was holding on to that initial hydrogen. Okay? So if I add that arrow, what's the result?
Lone pair,
Awesome.
negative charge on that carbon.
Negative charge on that carbon, and
Positive hydrogen.
I'd have the positive hydrogen floating around. So that would explain hydrogen just falling off the structure. Ta-da, there it is. Hydrogens don't do that very well. Why not?
Unstable.
You've seen lots of H+ before. Why do hydrogens, generally speaking, not just fall off of molecules? Whereas chlorides, on the other hand, will fall off kind of willy-nilly.
It's extremely unstable. For
H+, we've seen that before.
I mean, isn't it 99%? Right.
Yeah, you bring in isotope effects, don't do that. What's the difference between the H carbon bond and the Cl carbon bond?
Losing and gaining.
Somebody mumbled something over here. The difference in electronegativity between the relative atoms, which is ultimately another way of saying the carbon-chlorine bond is a polar covalent bond. The carbon-hydrogen bond is non-polar covalent. Because it is non-polar covalent, does it want to interact with anything? Nope. It's super happy where it's at. Those electrons are stable. It's not going anywhere. A polar covalent bond is a source of chemistry because that bond is polarized. We're trying to neutralize those charges. The whole process of chemistry is how do we neutralize those charges. Okay? So the carbon-hydrogen bond is a very tough bond to break because it's a non-polar covalent bond. The carbon-chlorine bond, being polar covalent, is already ready to just kind of fall apart. All we need to do is give it a slight push, and that thing's going to pop off. Okay? If it's not an easy bond to break, if it's not easy to form this H+, what could I add to force the H+ to come off? That looks good. What did my purple structure act as? Okay, where my purple arrow is, what did this structure act as to go to those products?
What was the question?
What did this molecule act as to make this? It acted as an acid, because what do acids do? Donate H+. You mean it's giving up H+? Yeah, this is acting as an acid. If I want that H+ to come off, what might I react this with? A base. What the hell is a negative nitrogen acting as? It's a base. Okay? That amide is explicitly there to help pull that hydrogen off. That's why it's present. So we could go through and have that NH2 with its negative charge come in, rip that hydrogen off. That's going to cause that bond to break. I'm going to get the negative on my carbon and my positive on my hydrogen. Of course this isn't right. What am I missing? In red.
The chlorine. Or,
Technically the chlorine's in red too, but no.
the positive charge.
The positive charge. If we look at what's happened so far, the red arrow showed what? Chlorine leaving. You mean the loss of the leaving group, yes? Yes. What did the purple arrow show?
An acid-base reaction.
You mean the loss of the H+ from my overall reaction. Okay, so have I done an elimination? I said those were the two things that need to happen, right?
I mean, there's one more.
There's technically another part to it. Okay, I have to gain a pi bond. Could I gain a pi bond from this? How do I gain a pi bond? What do you want to do to make a pi bond from this structure? Resonance, okay. Let's take that negative and let's put it right here. Can I do that move?
No.
Why not?
Two hydrogen block.
How about I move it this way then?
You change which hydrogen is taken out?
Also bad because I, again, exceed the octet. Maybe what I should do is think a little bit more critically about the hydrogen I remove. The hydrogen I want to remove needs to be in such a place that I can place that negative so that it could do resonance with the positive, and that resonance would result in the formation of a pi bond. So how about let's not remove that hydrogen. Let's remove this hydrogen. How do I need to do that? I take my base. Oh, what the? Don't, whatever you're trying to do, stop it. Oh my God. Go away. It's still there? Okay. I'm going to take my arrow and I'm going to have it attack that hydrogen. But that's a long arrow. Who gives a flying rat? But whether it's a long arrow or a short arrow, it's still doing the exact same thing. What's going to happen to the electrons in that bond? Give you two explanations. Right? We've got the electrons in that bond between the hydrogen and the carbon. What's going to happen to those electrons?
Go to the
Positive.
Okay, they're going to go to the atom. We're going to come back to you because you're more right. Not that you're more wrong, but
Just gonna resonate.
there's our negative. There's our positive. Now what could happen? We could go, oh, I can do resonance. And in that resonance, what have I shown? The formation of my pi bond. Beginning to end, what has happened? I've lost the hydrogen, I've lost the leaving group, and I've gained the formation of the pi bond. Okay? But we've got to backtrack through some of this. How many steps have I shown to do this?
3.
You should be able to do better than a lot. It's actually less than 3. It's actually only 2. There's step 1, there's step 2. This one was resonance, so it's not officially a step. Okay? How many steps was I required to do it in? Just one. Why? That's what an E2 mechanism is. All of that stuff has to happen at the exact same instant. So I have to take all of those arrows and somehow jam them all into one happy-go-lucky space. Right? Does the leaving group need to leave? Yes, so that arrow is perfectly acceptable. Okay? Does the hydrogen need to be removed? Yes. So I need my base to come in with its electrons here. Where do I want those electrons in that carbon-hydrogen bond to go? Okay. There were 2 parties that answered that question because it's the exact same question we asked like 30 seconds ago, and we had 2 people answer it. We had Andrew say, I want to go to the atom. And then we had Tyler say, I want to go to the bond. Okay. If we go to the atom, what do we produce? A system where we can do resonance. Which structure is correct in resonance?
Or left.
Both. Both are right. Because that's the definition of resonance. But one is more right, unfortunately, particularly when it comes to mechanisms. When we draw out our mechanisms are intended to draw always the most stable structure possible. And if we compare these 2 resonance structures, our blue and our black here, the black one is missing an octet, which means it is not as good as the blue one. Which means the arrows that I want to show in my single mechanistic step need to result in that final blue product, which means where should the electrons in that bond between the carbon and the hydrogen go? To the bond. So I will take the electrons from that bond and I will immediately shuttle them to the bond where I want the pi bond to form. What happens now with all of those arrows? Well, I can erase all of this stuff. And my resulting structure is that. What I have done is an E2 elimination involving sodium or amide. It's not saying sodium, but amide. Right? Do they need to tell us amide? Probably, because you need the base to pick up the hydrogen to do the E2 elimination. So they had to specify that in H2 so that you knew what to do there. Does that make sense? 15 minutes and we did 1/3 of the question. Okay? How fast should this become? Like second nature. It'll be like breathing, hopefully, in a matter of weeks. Okay? Because of the amount of practice that you go through in manipulating these things. Okay? Particularly for the E2. Okay? Not because you're going to practice all of the mechanistic steps, but we're going to look very specifically at the substitution and elimination mechanisms in detail. And because you're looking at them in detail, that's where you're going to pick up the reflex to draw them out really, really, really quickly. Okay? Kind of, sort of? So what do we move to?
Elimination. Or addition.
Now what we would go through and do is the electrophile addition of Br positive. What the hell?
Is it,
Oh, that's the other one.
this one's saying I'm wrong. Is that chlorine's wrong?
Yeah. Why is that chlorine wrong? So for the record, someone just popped up, was live action solving it. That's lovely. That's the point of this. You should be able to go through and solve. They're like, I'm wrong. I drew everything you drew. Except they did draw everything that I drew, but what did I forget? Lone pair electrons on that chlorine. Right? And if it's still telling you that it's wrong, it's following through a different issue that I would have to play around with. Where'd you? No, that should be good. See? Look at that. Oh, you already did all the rest. Okay. Electrophile addition of BR positive. What does electrophile addition mean?
Addition just means
Cool. I've got an addition. What does addition mean?
a pi bond raised into two sigma bonds.
Loss of a pi bond and gain of 2 sigma. Okay, that gain of 2 sigma can come in a little bit tricky, so we can get a little bit more nuance behind that gain of your 2 sigma. Is that always going to be true? Yeah, it will always be true. Take a look at the pi bond forming. Can you draw a resonance? Yes, we just had it drawn up. Where am I going to gain 2 sigma bonds?
The resonating pi bond that we
You're getting more accurate but less detailed on what I wanted here. Where am I going to gain the 2 sigma bonds? Where I have a positive and where I have a negative, which means one of the sigma bonds is going to need to bring in a molecule that is negative, and the other one is going to bring in a molecule that is positive. So if I can identify those charges, that can help me navigate the full addition. That's kind of neat. But we got to take a step back from that, because while the addition is the loss of a pi bond and gain of 2 sigma, are we doing an addition reaction? We're doing an electrophile addition. We're only doing part of the addition. The part of the addition that we're doing involves the electrophile. Well, what would the electrophile look like? Break down the name, electrophile. Phile sounds like our liking aspect, and electro is electrons, which means our electrophile should be positively charged. So what we're talking about for the electrophile addition is I'm going to gain the sigma bond that gains to the electrophile, my positive atom. Okay? Do I know where the electrons would come from to make the bond with the electrophile? Yeah? Where should they come from?
Never mind. I don't know.
Okay? So you might be saying bromine because you've seen bromine listed up here. Be real careful with that bromine. Is that bromine? That's Br positive. Br positive is actually missing electrons. And if it is missing electrons, would that be my source of electrons?
No.
No. That Br positive is actually going to be my electrophile. Where do I get the electrons to make the bond with the electrophile? I have to go back to my starting molecule and say, well, where do I have electrons? The only place that's readily accessible for electrons would be the pi bond. So what can I do? I go from my pi bond and I point them at that bromine. What's the resulting structure look like? Draw it out. Okay, so some pieces that are important to come out of this. Okay, first and foremost, your arrows tell you what to do. All too commonly, what students will go through and do is go, oh, I know what this is supposed to be. So they draw the product, and then they start moving stuff around wherever they want it to be within the product. And then they go, oh, let me change the arrow to be what I wanted. No, the arrow was correct. Your product must reflect what the arrow shows. Full stop. That's how it works. Right? You don't get to just jump to whatever product you want. The arrows are the instructions that tell you how to do the chemistry. Okay? And this is a place where you get some different emphasis within an individual class. My particular class pushes the hell out of manipulating the arrows because it allows you to predict without having to memorize what the product should look like. Why is that a big deal? 90% of students that try to memorize the product that comes out of it memorize it wrong. And the more reactions we add, the more times you screw up that memorization, which is why exam scores typically for OChem start mediocre and progressively get worse and worse and worse all the way through second semester. And that's because what's happened is you've tried to memorize instead of apply the content. Okay? And again, full disclosure, you can't just apply everything because it takes too much time. You have to find a balance. Okay? So in this case, all I'm drawing out is the things that didn't change. Okay, I know I still have that pentane, cyclopentane, so I'm drawing that. I still have the bromine with the 3 lone pairs. But what am I showing happening? I'm taking the electrons in that pi bond and I'm moving them. Okay, where am I moving them? Well, that's what the arrow is telling me. Now we have another interpretation we have to be careful of with what the arrows mean. Arrows are talking about the sharing of electrons. And if I'm sharing electrons, those 2 electrons between the bromine and something else. I'm sharing it with one of those carbons. Which carbon? The negative one. Which one was negative? Elaborate.
They both have one hydrogen between the pi bonds, so if you break that pi bond, they're both have a negative charge, and then
Not quite, but you got the right idea. Is there a difference between those carbons? No. If we look at that structure, so you're talking about going back to the previous one, so you're talking about a difference between these carbons. Are those carbons, those purple dots that I just drew in up here, are those the ones reacting with the bromide? Nope. So I don't care about that one. That's not there anymore. What's there is that black structure. What is the difference between those carbons? Silence is a pretty good answer. There isn't a difference. So it doesn't matter where I show those electrons sharing between the bromine and the carbon. I can show them here, or I could have just as easily shown them here. There is no difference between those carbons. Absolutely zero. Both of those are valid ways to draw that representation. How do you know? Tell me the difference between those 2 molecules. Go back to our chirality chapter and figure out the relationship. And what are you going to find out? They're identical. Right? That's why we talk about chirality. Okay? So cool, done. We can move on to the next one, right? What did I miss?
positive charge on the
Those 2 electrons moved into making the bond. Which means this bottom carbon has now lost electrons, and it is positively charged. You have to account for each of those pieces as you navigate. Why do you need to account for that? What's the very next step? Coordination of Br minus. And what does that Br minus need to find? A positive. And if you didn't account for that cation, where's your positive? You're now missing some information to be able to navigate that next step. So what happens in the next step? I have Br minus. And what happens? I take the electrons from my minus and I share it with the positive. And what do I end up with? And I now have the final system. And you have to navigate through each of those individual stages painfully slowly until you're comfortable with what's happening before you start skipping steps. Okay? And I would argue as soon as you skip steps, you're going to screw it up. Okay? What we're talking about is the mechanism behind this. That mechanism becomes super important because it dictates lots of relevant pieces of information, okay, that could come in as we dig into those mechanisms. For instance, what is special about those 2 carbons in your product? Call it the green dot and that green dot. What is special about them? They do have partial positives. That's useful. How many distinguishable groups are connected to each of those carbons?
2.
Try again. Try again. There's 4 distinguishable groups connected to each of those carbons, which means those 2 carbons are chiral atoms, which means, what do we need to worry about? Enantiomers, diastereomers, is one R, is one S. What is the relationship? Is one of them wedged and one dashed? Are they both wedged? Are they both dashed? All of that information comes out by critically evaluating each of the steps of the mechanism. Okay? Do you need to worry about that yet? No? Why not? We're not critically evaluating each of the steps of the mechanism. What we're trying to address right now is what are the fundamental pieces. Once we have the fundamental pieces, we can start to layer in those critical aspects. Okay? So don't panic about chirality yet, but you should be able to look at a structure and be like, I'm going to see chirality come back and bite me in the ass. Okay? And what do we now have, beginning to end? We have the answer. As long as you have counted for all of your electrons, you should be good all the way through this. Make sense? Did you want to look at an E1, or were you specifically concerned about the E2? Because you did ask for elimination.
No. Nucleophilic addition.
Okay, different question. Are there questions about what's up here?
E1 and E2 look the same thing, it's just you're moving one less for E1, but you don't have to do it with that.
So there's a good question. And I'll try and do it quick-ish, which will be relevant for people in the lab, because we'll talk about it. What chemical reaction happened? Sorry, let's try that again. That was... I'll try and balance it. What chemical reaction happened? Cool, substitution. What happened in the substitution?
You have electrons left and counter gain.
Okay. Loss of the leaving group, gain of the nucleophile. If I do those 2 steps at the same time, so simultaneous, there's that word, it's SN2. If I break those down into individual steps and make it stepwise, the collection of the stepwise mechanisms is known as an SN1. Okay? What does the collection mean? Officially, the loss of the leaving group would be a heterolysis, because all you've done is break that bond to a non-hydrogen. Okay? And then the gain of the nucleophile would be a coordination. When I do those 2 mechanistic steps in sequence, that is what's known as an SN1. So the 1 and the 2 have reference to how the mechanism is working. When we talk about chapter 7, we don't hear SN1 because SN1 isn't officially a mechanistic step. It's a collection of mechanistic steps that we've decided to name. And we also call a mechanism, confusingly enough. Okay? Why the 1 and the 2? Well, the 2 we already addressed was bimolecular. What does the 1 mean? If 2 meant bimolecular, what do you think 1 means? Unimolecular. So again, if you looked at the rate expression, what you would see is only 1 species in the rate
So
expression.
would that one happen first? I don't.
Say again?
Would that happen first in the reaction, or
I don't know how to answer your question.
Just one-
So if we're going to talk about the SN1, which one happens first? Heterolysis will happen first, then the coordination. Okay, and again, when we talk through it in lab this week, we'll talk through why. Exit that. You said, which one did you say? There we go. Oh, but you haven't attempted it. Since you haven't even opened it, I can't look at it. Oh, that's interesting. I looked at the other one, though. Which one, Tyler? I apologize for calling you Zach.
There are 5.
5? Should be. As long as you've looked at it within a pool, I should be able to open it. If you haven't looked at it, I don't think I can. So if we go through and run a nucleophile addition, let's break down the terms. Nucleophilic addition, what does nucleophilic mean?
To give electrons.
Okay, this is a thing that needs to give electrons. What would be a characteristic of something that gave electrons? What would it need to have? Come back to, you're technically both right. The more electrons is more appropriate. Okay, negative charge, not necessarily. Typically, yes, at this stage, because we're trying to keep it simple. Okay, so typically what I would do is N for nucleophile, and I draw that lone pair. Okay, if you want to add the minus, you can. It does not have to be negatively charged. Okay, what did the addition mean? Make it a little Christmassy.
Pi bond breaks.
Okay.
Forming 2 sigma bonds.
Loss of the pi bond, okay, and form 2 sigma. Okay, if we're talking about that pi bond, if we looked at resonance on that pi bond, we'd have a positive and a negative here. Right? That's addition overall. We're talking about the sigma forming to both the positive and the negative. This isn't looking at the addition reaction, it's looking at the addition mechanism. So we have to be a little bit more careful about what we're talking about forming. We're reacting it as a nucleophile addition, which means the nucleophile needs to react with my pi bond. Where is it going to react? At the positive atom, because the nucleophile was negative. Okay? So we're not talking about the formation of 2 sigma bonds. We're really only talking about the formation of 1 sigma bond, and it's the sigma bond on our carbon positive. Trying to think of proper wording I want to use there. We'll call it our positive substrate, our positive pi substrate. Okay, and we know it's forming at the positive because we're reacting it with a nucleophile. Make sense? Okay, so we now go back to our reaction down here. Okay, we need to react. Okay, what thing is the most reactive? Okay, a couple people in the back are squinting, so we'll make it harder and just erase everything so you can't see it. Oh, I already forgot what the structure was. Was it hydrogens?
Yeah.
What's the most reactive thing?
Carbon anion.
Oh, fancy. Okay, yes, the carboanion or the carbanion. You could also just say the negative carbon. The charged thing is the most reactive. Okay, because it is negatively charged, which do you think it's acting as? The nucleophile or our pi bond substrate? Because the nucleophile needed to have extra electrons, this makes a whole lot of sense that this is going to be the nucleophile. That nucleophile needs to share with a positive thing in our pi bond substrate. Where do we see a positive in our pi bond substrate?
So we need
Not yet. I don't see a pi bond, or sorry, a positive. Do you see a pi bond? Yes, okay. So one of the things that we could do is look to that pi bond and remember that pi bonds have some interesting chemistry. That interesting chemistry is resonance. So the instant you look at that structure, what you should actually be seeing would be that. And that becomes really powerful because if you see that, where do you think the negative needs to react? On the positive carbon. So what has to happen? That attacks. Okay? But this is where we have to be careful with our imagination. So ideally we've done that resonance practice that we're imagining the structure and we didn't have to draw it because this is a bad or a worse resonance structure. What I need to be doing for my mechanism's sake is to make sure I draw it from the best resonance structure, which would be that one. But if I just do this single arrow, what would I result in for my answer?
Your carbon would have its octet exceeded.
My carbon would exceed the octet, which would then be
Correct.
incorrect. So what do I have to do to fix it?
Show the arrow of the pi bond onto the oxygen.
That pi bond, we have to show where that pi bond's moving and where does it need to move? Away from the exceeded octet problem, which means up towards the oxygen. The net result, the rest of the carbon backbone did not change. I still have that sigma bond to the oxygen. Whoops, color code. I now have that red bond. And if we really wanted to, we could show those 3 hydrogens. We still have the black lone pairs, and we've now gained another lone pair to that oxygen. And we now have our potential answer, and of course it tells us we're wrong because we forgot to include the negative charge on the oxygen. And what have we now done? We've completed a nucleophile addition, okay, or a nucleophilic addition. We used a nucleophile to add to a pi bond. And the last reaction we looked at an electrophile addition. We used an electrophile to add to the pi bond. Okay? So they're kind of opposites of each other as far as the reactivity goes. So in the electrophile addition, our end product ends up being positive, okay, or intermediate. In the nucleophile addition, our end product ends up being negative. Does it make sense? Well, if I add a negative thing to a structure, what should happen to its charge? It should become negative. And if I add a positive thing to a structure, it should become positively charged. So it internally checks out within those systems. Does that make sense? Questions? Okay. Again, we're trying to break this down according to some of those pieces that we've already talked about. We're talking about the nucleophile, we're talking about the addition, we're following those pieces. What I'm trying to do is provide that larger context. Most of what you're doing in Chapter 7 is just you've got examples of what all of those mechanistic steps are. Want to say like 10 to 11 different mechanistic steps. Okay? And what you would do is, oh, it says nucleophile addition. Let me find the nucleophile addition one. What did they do? Now let me match across. Okay? And one of the problems that you have to be aware of is that a subtle change in the structure can flip you the hell out and get you all sorts of confused. Okay? For instance, let's do this same reaction, right? I want to do a nucleophile addition, but now I want to do a nucleophile addition. Let's just go all in. Why not? Nucleophile addition. Exact same thing. You should be able to draw out the product now, or at least the curved arrows, in a matter of seconds. Laughter is kind of the response I was going for on this. Time's up. What's the problem? You're good at sharing. What's the problem?
We got a lot of pi bonds here, and we're doing nucleophilic addition, right?
Mm-hmm.
So I'm just saying we do the pi bond connected to the oxygen as our.
Okay. So that's interesting. Just in the process of you talking through that, I don't know if anybody knows. It's like, oh, there's a lot of pi bonds here, so all this is really hard. We're just going to use the oxygen.
Yeah.
Why'd you ignore all the other pi bonds?
Because it just seems easier this way. I just put it there.
Okay? Which is perfectly acceptable. One of the things that you should be starting to look for is patterns within that. What's the difference between the pi bond between the carbon and the oxygen and the carbon in the rings? They all have the same hybridization. So one option, the ring has resonance. Remember, resonance is something that should be at the back of your mind. If I've got resonance, what does that do to those pi bonds? Stabilizes them. And if they're stable, not going to react. Okay? Lean into it more. Even more basic than resonance. And if you just said acidity, I realized that basicity was... Electronegativity, what do you mean? Oxygen is more electronegative than carbon, which means the carbon-oxygen double bond is a polar covalent bond. Because it's a polar covalent bond, that immediately makes it more reactive. What about the pi bonds in the rest of the ring? Carbon-carbon double bonds. Those are not polar covalent. Those are non-polar covalent. Those should immediately fall to the bottom of your list as far as reactivity. All of those things are thoughts that should be sitting in the back of your head. You've been given the context to be able to hold them. This is where organic chemistry becomes organic chemistry. Everything we've talked about up to this point was just how do we draw this and label these things and talk about these pieces. Now you're actually trying to say, well, how should they react? Why does all that stuff I learned apply now? Okay? This is the meat of OChem. How do you apply everything? And that's where things become challenging, and that's where things become fun, because it becomes a puzzle. How could you puzzle through all of these things? Okay? This should be my negative. That should be my nucleophile. What does the negative need to react with? A positive. How do things become positive?
By losing electrons.
True.
Yeah.
If I look at a general structure, do I see a positive in my starting structure?
No.
Chlorine could be a leaving group. Chlorine's electronegative. It could suck electrons away from the carbon because chlorine is more electronegative than the carbon, which generates a partial negative on the chlorine and a partial positive on the carbon. By that same token, isn't the oxygen more electronegative than the carbon? So the oxygen's partially negative, making that carbon even more partially positive. Do I get any of that effect on my carbons of the pi bonds or my alkenes? Nope, which means what's my negative going to react with? That carbonyl carbon. That's the most positive thing. What you're just trying to find is positives and negatives and put them together. That is all we do. Depending on where the positive or negative is, it changes the name of the mechanism, but that's it. Okay? Start processing this stuff and organizing it. You will find that it'll start to come together and these pieces will start to make sense. The sooner you can recognize that all we're doing is attaching positives to negatives, the sooner this class becomes insanely tedious. Which I shouldn't tell you, but I just told you. Okay? Because everything we do is finding a positive, finding a negative, and we put it together and that's it. That's all organic chemistry is. Okay? In few select cases, we do something interesting that's outside of that realm. Vast majority of the time, that's all it is. With that, I'm done.